All right, I'm back. I know that felt like a long time for you. So I'm going to actually go to section 6.5. We're only going to do 3 examples. They're not huge, and it's actually stuff you already know. Even if you don't think you know it, it's back in your brain somewhere. Somewhere back there. It's back there. Just a sec. I'm running out of black markers. I'm gonna have to send my husband to Staples for an emergency marker run. All right, so this one talks about, we've done vertical asymptotes. Now they're gonna talk about horizontal and oblique asymptotes. We're not doing oblique asymptotes today. I'm saving those for tomorrow. We're just going to look at horizontal asymptotes today. You've done horizontal asymptotes before. Again, the language that they use is slightly different, but that's okay. It's still the same thing. So a horizontal asymptote is one where as you go to the extreme ends of the x-axis, the graph will have an asymptote there, and the graph will be approaching it. So let's say that you had a horizontal asymptote at x is equal to 0. As you get further and further out, the graph will be approaching that asymptote. So again, they talk about this in terms of limits, but the limit for this looks a little different than the limit for a vertical asymptote, because in the vertical asymptote, in the example in the question I just did in the previous video, when I did 4b, it said, what is the limit as x approaches 2? What is the limit? In this case, when we talk about limits in terms of a horizontal asymptote, we would express it this way. My limit as x approaches infinity. So positive infinity would be that way, negative infinity would be this way. So what is my limit as my x approaches infinity? So as I get further to the end of this graph, I get further along the x-axis, what is my graph approaching? Well, my graph is actually approaching 0, right? That's the height it's approaching. It's approaching 0. So as my x gets further and further out, same thing, what is my limit as x approaches negative infinity? As I go further out here, it's approaching 0. Really what they're asking you is, where is the horizontal asymptote? Well, my horizontal asymptote is at y is equal to 0. The limit is where the asymptote is. Now, the funny thing about graphing a horizontal asymptote, and I haven't told you this before, or if I did, it was a passing comment, so you don't remember. Horizontal asymptotes don't work like vertical asymptotes do. Vertical asymptotes, the graph can never, ever, 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 ever cross that asymptote, ever. Nowhere along that asymptote can the graph cross it. That's not actually true for a horizontal asymptote. For a horizontal asymptote, as we get to the extreme ends of the graph, it's not going to cross, but it is possible, and it would be a weird case. You're not going to see it very often, but just so you know it exists. Again, it doesn't happen very often. I'm not going to be expecting you to know that it does this. I'm not going to be giving you ones and saying graph it and it's going to do something wonky in the middle. But it is possible that it could do something like this. So it could actually cross the horizontal asymptote in the middle, but at the ends it cannot. At the ends it cannot. So that's where it can't. All right? But you're not going to see that very often. Don't worry about that. I just want you to be aware, if you see one, if you see a picture of a graph and it is crossing a horizontal asymptote in this middle part somewhere, it can do that. It's at the very ends. It's at the extreme either end of the x-axis that it can't cross the horizontal asymptote. All right. So I gave you rules for horizontal asymptotes before. I want to say, yeah, in grade 12, in the first semester, I gave you some rules about horizontal asymptotes. They have them in blue on page 352, but again, the way they word it is kind of awkward, but I will explain. So here's how they word it. They say the limit as x approaches infinity for 1 over x to the r is equal to 0, and the limit as x approaches negative infinity for 1 over x to the r is also 0. Looks confusing. Really, all they're saying is if you have a variable that has an exponent on the bottom, and on the top all you have is a coefficient, you will always have a horizontal asymptote at 0. I gave you a rule that applies to this that basically said, it said this: if the degree, and remember what degree means the exponent on a variable. So if the exponent on the variable of the denominator is bigger than the numerator, then there is a horizontal asymptote at x is equal to 0. That's how we worded it in grade 12. This is actually saying exactly the same thing, but it is saying it in calculus words. All right? So basically what we're saying is if the degree of the denominator, so if it's like 1 over x squared, well, 2 is the degree on the bottom, 0, because there is no variable, is the degree on the top. Therefore, there is a horizontal asymptote at 0. So in example number 2, yes, I skipped example 1 because I could. In example number 2 on page 352, here is what they say. Oh, I'm going to leave that up there. The limit as x approaches infinity for 1 over x to the r is 0, because I want you to see kind of how they're applying that. A photocopying store. So if you go into Staples and you hand them a flyer or something and you say, I want you to make 500 copies for me. All right, so how they do that is they charge a flat rate of $2 plus then they charge 5 cents for every copy that you make. So it says write a function to represent the average cost per copy. So the cost per copy is $2 plus 5 cents per copy. Now if I want to find the average cost per sheet, so if I ask them to do 500 copies, I could figure out the total cost by doing 2 times 0.05 times 500. But if I wanted to know how much am I paying per sheet that they're doing, then I would divide by the number of copies I make. You intuitively understand this because if I said the charge is $2 plus 5 cents for every single flyer that you make, and you're going to make 2 flyers, you understand that you're not getting as good a deal as if you're making 1,000, because that flat rate of $2 has to be divided up among all the different copies that you make, right? And so if you're only making 1 or 2 copies, that $2 makes a big difference to your price. But if you're making 1,000 copies and you don't really care about that toonie at the beginning, it doesn't make any difference. So this is my average cost. Now, they say determine the limit as x approaches infinity, and then explain what that actually means in real life. So I'm gonna show you how we're gonna do that, how they show you to do that. They show you to do that by doing this. If I break this up, this x is underneath both of those pieces. So I could break this up and say 2 over x plus 0.05 x over x. I could do that, all right? And then what I could do is I could actually cancel out these two x's, and I have 2 over x plus 0.05. So I have two pieces. So if I want to find the limit as x approaches infinity, I want to find the limit as x approaches infinity for this piece, and I want to find the limit as x approaches infinity for this piece. Well, let's take this piece first because it's easy. My limit as x approaches infinity, well, there is no x in this piece. So this doesn't actually make any difference at all. This is just 0.05. But my limit as x approaches infinity here, you can think of this a couple of different ways. I can think of 3. So first off, this is exactly like this, 1 over x to the r, a constant over x to the something. Here is a constant over x to the something. It is automatically 0. It's automatically 0. Think of this another way. If x is approaching infinity, that means x is a really big number, like 1,000 or 1,000,000. If I take 2 and I divide it by 1,000,000, I'm going to get an answer that is so close to 0, it might as well be 0. In fact, if you put 2 divided by 1,000,000 in your calculator, it will likely just tell you 0 because it's so close that your calculator doesn't even differentiate it. Another way you can think of it is if the degree of the denominator is bigger than the numerator, and the degree here is 1, the degree here is nothing because there isn't an x, then x is equal to 0. There's a horizontal asymptote at 0, so the limit is 0. Sorry, at x is equal to 0, so it's 0. So the limit as x approaches infinity is 0 plus 0.05, which is 0.05. So that's my answer. Don't worry about this too much. I'm not going to ask you to do a whole lot like this, but I just want you to think about what does that mean in terms of real life. What they're saying is that if your x, which is your number of copies, if your number of copies is very, very, very large, then really you're paying about 5 cents per copy because that $2 is now going to be irrelevant. It's not going to make any difference. And like I just got done explaining, if you go in and they say, yeah, I can make 1 copy of that sheet for you, but it's $2 plus 10 cents for every, or 5 cents in this case, for every sheet that I make, so it's $2.05. You're going to go, $2.05 for 1 sheet of paper? That seems like a lot. But if you're coming in and you're saying, I need 1,000 copies of this flyer, and they go, okay, well, it's 5 cents per copy, but there's also a $2 flat fee for just using our photocopier, you're going to go, well, the $2 doesn't really matter because you're making so many copies. So that's what they're talking about here. All right. So if the degree of the denominator is bigger than the degree of the numerator, then there's automatically a horizontal asymptote at 0. In other words, the limit will be 0. Okay, if you're talking about it in terms of limits, it will be this. My limit as x approaches infinity is 0, as long as the degree of the denominator is bigger than the degree of the numerator. Now, in example 2, they want you to evaluate the limit, or sorry, example 3. It's example 2 for me because this is the second one I'm doing, but it's so anyway, 352, bottom of it. The limit as x approaches infinity for 10x squared minus 2x minus 1 over 5x squared minus 3x plus 1. Now, they go through a whole lot of work to show you how you would come up with an answer for this. And let me explain what they do. Let me explain what they do, okay? They divide every single piece by whatever the variable with the largest exponent is. So x squared is the largest exponent. So they go through and they do this. 10x squared over x squared minus 2x over x squared minus 1 over x squared, all divided by 5x squared over x squared minus 3x over x squared plus 1 over x squared. So that this x squared will cancel this x squared, and I just have 10. This x will cancel one of those x, and I have minus 2 over x. Nothing cancels there, and I have 1 over x squared. That's what I have on the top. And on the bottom, this x squared cancels this x squared, so I just have 5. This x will cancel one of these x's, so I have 3 over x plus 1 over x squared. Now, I want my limit as x approaches infinity. I'm going to look at that for each of these things separately. Okay, so my limit as x approaches infinity for this is still just 10, because there is no x to approach infinity. There is no x in that piece right there, so it's just 10. 2 over x. Again, if I have a constant over an x, it's automatically 0. Don't care what exponent is on it. Could be 1, could be 500. If I have a constant over an x, the limit as x approaches infinity is always 0. So for this, my limit as x approaches infinity is 0. Same thing for this one. I have a constant over x squared. That's going to be 0. Here, it's just 5 because there is no variable. Here, it's 3 over x, so that's automatically 0, and plus 0. So what do I end up with? I end up with 10 over 5, which is 2. Sorry, which is 2. So my limit as x approaches infinity is 2. This seems like a lot of work, and it is, and it's confusing. Let me give you the short version. You already know the rule. I gave it to you in grade 12. In grade 12, when we were talking about horizontal asymptotes, I said this. I said, if the degree of the denominator, I'm going to shorten it, denominator, is smaller than, or sorry, not less, my apologies, is the same as the numerator. I don't know why I spelled that whole thing out. And it is, right? The highest exponent on the top is squared. The highest exponent on the bottom is also squared. If the degree of the denominator is the same as the numerator, now this takes a little bit of explaining, but what I said was take the leading coefficients. I don't know if I spelled that right. Find the leading coefficients. So let me explain again, because we did this in grade 12, but let me explain again what that means. I have an x squared over an x squared. That's the highest exponent on the top. That's the highest exponent on the bottom. Take the coefficients, take the numbers in front of that. 10 over 5, which is 2, which was the answer I had way down here when I was doing all that fancy stuff. You don't need to do all that fancy stuff. If the degree on the top and the bottom are the same, take the coefficients in front of those, 10 over 5, that's the limit. The limit is 2. That's it. That's all I'm doing today. I'm not doing anything else. I will post a few questions for you to do. Hopefully going over that homework for concavity helped. Again, at the end of all this, or even when we get to section 6.6, they put everything together. If we find at that point you're struggling, maybe what we'll do is we'll do like a live Q&A session or something like that, okay? We'll see how all that goes. All right, I will talk to you again. I'll talk at you, I don't know, soon. See ya.